Hi, this is Nathan O. Schmidt. I fed in 2 of my tricorder framework preprints into Google's Gemini AI to generate an audio report discussion. Now this one's about 40 minutes long, and it does a pretty good job of explaining the content in a fun way, so I figured that I would share this with you. The first paper I fed in was the tricorder framework, unifying complex coordinates with topological and reflective duality across circles of any radius, as a prerequisite to the second paper, which is then the main focus of the discussion, the tricorder framework, radial dual triangular lattice graphs with exact bijective dualities and equivariant encodings via the inverse hexagonal dihedral symmetry group T24. So yeah, let's get to it and enjoy. Maybe we'll learn a thing or two.
Okay, let's unpack this. Today, we are undertaking a deep dive into what we believe is, well, a truly foundational piece of mathematical and computational research. It's by Nathan O. Schmidt. This novel mathematical structure he calls the tricorder framework. This work, it really feels like a serious attempt to bridge, the elegant, continuous world of geometry and topology with the gritty, practical demands of digital computation.
It's definitely compelling work, and it's worth noting the author's trajectory here. Nathan O. Schmidt, he has this serious background in both computer science and mathematics. His research covers some fascinating areas, like machine learning, physics. Actually, he has published work tracing back to 2012 focused on the complex domain of quark confinement,
right,
and even cryptography.
Right.
What makes these recent papers particularly interesting, though, is that they mark his return to publishing after an 8-year research pause. So this isn't just some minor tweak to an existing theory. It really feels like Schmidt is laying down a completely new foundation, probably based on years of, well, deep thinking.
Absolutely. And our mission for this deep dive is really to guide you through the framework's core mechanics. We need to understand how it conceptually unifies these different mathematical domains, geometry, topology, and the rules of computation. And crucially, we need to show how this unification translates into, well, highly efficient digital applications. Schmidt is fundamentally redefining how we partition and navigate spaces, specifically those based on circular symmetry, which, let's face it, is everywhere in computing and physics.
That really is the core innovation, isn't it? If you think about the standard complex plane, which is where, electrical engineering, quantum mechanics, signal processing, they all live there.
Yeah.
The simple geometric circle is usually just treated as a passive boundary. It's just a line you cross over. Schmidt transforms that line into what he calls an active separator with intrinsic properties that you can actually exploit.
Active separator, I like that.
And this activation, this making the boundary active, it leads to these really powerful symmetries, almost visual, recursive symmetries. They kind of remind you of M.C. Escher's artwork, And those symmetries, those are the source of the computational speedups we're going to talk about.
Okay, let's dig into that. We have to start with a continuous foundation, right, that's laid out in the first paper. To make his framework actually work, Schmidt first needed to sort of reformulate the way we describe a point in the complex plane. He introduces this generalized coordinate system, and it's designed specifically to unify the 3 classic forms we typically use. So complex number notation, the familiar Cartesian vector form, and polar coordinates.
Yeah, and this initial move, it might sound a bit subtle, but honestly, it unlocks everything else that follows. In standard math, the real component, let's say x sub r, it's just a number, a scalar. Schmidt treats x sub r and the imaginary component x sub I not merely as scalars, but as orthogonal axis-aligned Euclidean 2 vectors. That's the key.
Okay, wait. So the real part gets its own vector along the real axis, and the imaginary part gets its own vector along the imaginary axis.
Exactly. So the real component is assigned a vector, let's call it vector r, along the real axis, and the imaginary component gets vector I along the imaginary axis. They're orthogonal.
But why go through the trouble of formalizing something that seems kind of obvious? I mean, directionality is always implicit in Cartesian coordinates, isn't it?
It is implicit, yes, but formalizing it this way as explicit orthogonal vectors, it instantly forces you to deal with the inherent orthogonality. And most importantly, it provides this explicit formal handle on direction, which frankly is often quite messy to deal with consistently in standard notation.
Okay, I see. You make the directions explicit components.
Precisely. When you treat them as explicit vectors, you formalize the notion of, which way is up or which way is right for that specific component. And this formalization realization, it has a structural consequence. This coordinate system immediately excludes the origin, point 0.
Excludes the origin.
Yep.
Why?
Because directional assignments, where vector r and vector I meet, they are entirely undefined right at the point 0. There's no direction there. So the framework's analysis is therefore focused specifically on the relevant zones, the places where directional assignment and spatial partitioning are actually non-trivial.
Interesting. Focusing only where direction matters. And that focus on explicit directionality, that's what leads to this really distinctive feature, the structured orientation built using these phase pairs.
Exactly. If you look at traditional coordinate systems, that circle boundary is passive, partly because the directional information across different quadrants, it's inconsistent. Or it requires multiple checks, conditional logic, to figure out where you are. Schmidt solved this by assigning unique directional markers. He calls them phase pair, denoted by the Greek letter phi. And crucially, these assignments depend only on the signs of the real and imaginary components, x sub r and x sub I. Nothing else.
Okay, that's a truly neat trick. It's like a combinatorial encoding of the vector's direction. You're linking the algebraic quality, the sign, positive or negative, directly to the geometric property. It's angular direction in a single constant pair.
Let's walk through a quick example just to see how elegant it is. Take quadrant I. Both x sub r and x sub I are positive there. The phase pair is constant, always constant, at 0 pi over 2 sub phi.
So 0 for the positive real direction, pi over 2, 90 degrees for the positive imaginary direction.
Exactly. And that pair, 0 pi 2 sub phi, it holds constant for any vector, no matter its length, its magnitude, as long as it's somewhere in quadrant 1.
Okay, that's clear for inside a quadrant. But what happens when a vector lands exactly on an axis boundary? Because that's usually the part that breaks standard computational logic, right? The edge cases.
Right, the edge cases are messy, but this encoding, it actually solves that problem quite cleanly. Schmidt defines explicit, consistent rules for what happens when a component is exactly 0. For instance, on the east boundary, that's the positive real axis, the phase pair is defined as 0, 0 sub phi. On the north boundary, the positive imaginary axis, it's P2, P2 sub phi, and so on for west and south.
So it forces consistency even on the lines between quadrants.
Exactly. This choice ensures that the directional assignment transitions smoothly and consistently across the entire space. It removes the ambiguity. It makes the entire space, all 4 quadrants and all 4 axis boundaries, uniquely structured by direction.
Okay, so once that structured orientation, those phase pairs are established, the formal topology of the partition becomes rigid. And that leads directly to the name of the framework, right?
Precisely. The term triquarter comes from the fact that the framework partitions the complex plane, let's call it X, into a trichotomy, a fundamental division into 3 distinct topological zones. And this division is based on an arbitrary circle of radius r.
Okay, 3 zones.
Zone 1, the inner zone. Let's call it x minus r. That's where the vector norm, its length, is strictly less than r. Zone 2, the boundary zone, t sub r. That's the circle itself, where the norm equals r. Zone 3, the outer zone, x plus r, where the norm is strictly greater than r.
Inner, boundary, outer. A 3-zone partition applied across the 4 standard quadrants. Okay, I get the name now, triquarter. But why is this more significant than just defining a circle? People define circles all the time.
Because of the triquarter topological duality theorem, this is a key result. This theorem elevates the boundary circle, T sub r, from just being a passive line to being an active separator. Remember that term?
Right, active separator.
It proves that T sub r is topologically dual to both the inner zone and the outer zone. Think of it as a guaranteed, consistent separation between inside and outside. This theorem ensures that the inner radial direction, so your path approaching the circle from the inside, is distinctly and consistently separated from the outer radial direction, your path approaching from the outside, and the directional context provided by those constant phase pairs along any radial ray out from the origin that makes the separation rigorous and predictable. It's mathematically solid.
Okay. Now here's where it gets really interesting. This next concept sounds truly captivating and really speaks to the power of symmetry. Schmidt calls it the Escher triquarter reflective duality theorem. It's clearly drawing inspiration from M.C. Escher's art, where patterns flip and repeat and fill space perfectly.
And the mathematics is just as seamless, it's just as elegant. This reflective duality, it's achieved using a well-known tool from classical geometry, the circle inversion map. Schmidt denotes it as iota sub r. Now, inversion itself isn't new, but its specific application here within this framework, that's what's revolutionary.
Okay, walk us through what inversion actually does in this context. How does iota sub r work?
Right. So the map performs 3 crucial actions, building directly on the topological partition we just discussed. First, it fixes every single point that is already on the boundary circle T sub r. Those points don't move, they stay put. Second, it perfectly swaps the inner zone x minus r with the outer zone x plus r. Every point inside is mapped uniquely to a point outside and vice versa. It's a perfect exchange.
Swaps inside and outside.
Okay. Third, and this is really the mathematical punchline here, it preserves the directional phase pairs, phi.
Wait, hang on. You're saying if I have a vector deep in the outer zone, say quadrant 3, when I invert it using this map, it lands somewhere in the inner zone, but it's still encoded with the quadrant 3 phase pair. The directional properties don't change into the reflection.
Exactly that. The encoding, the directional information, is preserved. It's invariant under inversion. And because the inversion map, iota sub r, is an involution, meaning applying the map twice gets you right back where you started, it's its own inverse. It guarantees an exact bijection, a perfect one-to-one swap between the inner and outer zones while maintaining total directional consistency under that reflection.
Wow.
This creates an incredibly robust, precise, and ultimately exploitable symmetry. It transforms the space into this highly structured self-dual system. And this continuous foundation, this self-dual structure, is what all the computational efficiencies we're about to discuss are built upon.
Okay, perfect. So now we take that beautiful theoretical framework, the generalized coordinates, the explicit phase pair structure, the dualities, and we immediately check its practical performance. We need to see how it delivers actual, concrete computational advantages. And a really simple, common task is the perfect test case: quadrant-based transformations. This is where we see those elegant mathematical definitions translate directly into, well, saved CPU cycles.
Absolutely. This case study is essential for validation. You need to show it works in practice. And think about it, any algorithm that needs to process a stream of vectors and make decisions based on where those vectors lie, which quadrant, which axis boundary, it stands to benefit. Real-time signal processing, graphics rendering, simulations, anything requiring massive throughput.
Let's first talk about the pain point, the standard approach. If you, the programmer, have a complex vector and you need to apply a specific action, say, scale it up if it's in quadrant I, or maybe rotate it 90 degrees if it lands exactly on the positive imaginary axis. The conventional approach to classify that vector's location requires what's often called nested conditional logic. If this, then that, else if this.
Oh, yeah. And that nested logic is messy, and it's slow. The conventional method requires explicitly checking the signs of both the real component, x sub r, and the imaginary component, x sub I. That's the first step. But crucially, you then need separate, often elaborate nested checks just to handle the zero conditions for when the vector lands exactly on one of the 4 axes. You have to check, is xr positive? Then is xi positive? Okay, q1, else is xr 0. Then is xi positive? Okay, north axis, else it goes on and on.
It's a decision tree, basically. And the actual data Schmidt collected on this standard approach is, frankly, staggering. To classify a vector's location and apply the correct transformation, in the worst-case scenario, the standard approach requires up to 7 comparison conditional checks per vector.
7 checks. And let's think about why that's a worst-case scenario. Imagine you have a vector lying exactly on the negative real axis. That's on the boundary between Q2 and Q3. Your code has to first check. Is it in Q1? No. Is it in Q2? No. Is XR 0? No. Is XI positive? No. You might have to rule out almost all other possibilities, quadrant by quadrant, axis by axis, before you finally land on the specific rule for the negative real axis. This complex branching logic, it's just incredibly inefficient, and it's error-prone, especially right at those boundaries.
Yeah, one mistake in the logic for an axis case, and you get subtle bugs. And that inefficiency, it scales terribly. Every time you add another conditional check in that chain, you add latency, you reduce throughput. The triquarter framework, however, completely streamlines this logic. It uses that structured orientation, those phase pairs we established earlier.
And the efficiency advantage is what's phenomenal. It really is. With the triquarter method, you are not running complex nested logic trying to find the right quadrant rule in a big if-else chain. Instead, you only run simple checks to determine the sign and zero condition of x sub r. That's up to 2 checks maximum. Is it positive, negative, or 0? And you do the same for x sub I. Again, up to 2 checks maximum.
Okay, hold on. Why only up to 2 checks per component? Explain that.
Because the phase pair rules, remember, they depend only on the sign or 0 status. So for x sub r, you check. Is it positive? If yes, done, 1 check. No, is it 0? If yes, done, 2 checks. If no, it must be negative, still 2 checks total. Same logic for x sub I. So max 2 checks per component to determine its state, positive, negative, or 0.
Got it. Simple state check.
Once you establish which of those three states both x sub r and x sub I are in, you have immediately generated a unique phase pair, let's say 0, pi 2 sub phi for Q1. Once that unique phase pair is assigned, you simply use it as a key to access the corresponding transformation directly from a predefined lookup table or a map, like a dictionary. And that lookup, that's a constant time operation, O1. It happens almost instantly. No further comparisons, no further branching logic is needed at all.
So instead of that complicated decision tree with lots of branches, you've basically built a simple sign-in zero checker that points directly to the answer in a table.
Exactly. The geometry itself becomes the index, and the maximum check count drops dramatically. Schmidt's framework consistently reduces the required checks to a maximum of 4 comparison conditional checks per vector. And that's the maximum, regardless of whether it's deep inside a quadrant or sitting precisely on an axis boundary. 4 checks max.
Let's look at the gains on those tricky cases again. That vector on the negative real axis boundary, it required up to 7 checks in the standard model. Triquarter, only 4 checks. What about a vector in quadrant 2 or quadrant 4? Standard approach needed up to 5 checks. Triquarter needs only 3 checks in those cases.
You're looking at a guaranteed 30% to almost 50% reduction in conditional complexity, just in the worst case scenarios. Now, if you're designing high-speed electronics or real-time systems, a 50% reduction in conditional checks, that's like finding gold. It means superior computational performance, much higher throughput for streams of data, and probably lower energy consumption too, because you're just eliminating unnecessary processing steps.
It's a really powerful example, isn't it? How formalizing the geometry making, the underlying structure explicit through those generalized coordinates and phase pairs, directly simplifies the computational logic. It removes that inherent risk of inconsistent or ambiguous rules at the critical axis boundaries that just plagues the traditional nested if-else approach. The geometry itself, encoded in the phase pair, becomes the lookup key. Simple, fast, robust.
Precisely.
Okay, so what does this all mean for systems that actually operate digitally? While the continuous framework we just discussed is elegant, beautiful even, real-world computation, whether we're talking robotics, networking, cryptography, graphics rendering, it happens on discrete structures, usually lattice graphs, grids of points. The second paper Schmidt published is dedicated entirely to successfully extending the triquarter framework to exactly that, a discrete model. He calls it the radial dual triangular lattice graph, or lambda sub r.
Yeah, this transition from the continuous complex plane to a workable digital lattice, that's probably the most crucial implementation step. Nathan O. Schmidt needed a discrete structure, a grid that natively supported the symmetries he'd rigorously proved in the continuous domain. Specifically, that 6-fold rotational symmetry and that dual reflection symmetry from the inversion map.
And he chose the base triangular lattice, which is often called L. It's not the standard square grid most people picture first. Why is the triangular lattice the superior choice here? What's special about it?
It really boils down to 2 things: angle and connectivity. The triangular lattice is built on equilateral geometry. All its internal angles are 60 degrees. And this inherent 60-degree angular structure aligns perfectly with the order 6 rotational symmetry that's essential for exploiting circular symmetry properly.
Right, 60-degree turns get you back to the start.
Exactly. If you tried to use a standard square grid, you'd have 90-degree angles. They'd constantly mismatch the 6-fold symmetry you need. You could consider a hexagonal lattice that also has 6-fold symmetry elements, but it's often sparser. A triangular lattice usually offers more connections between nodes, giving you a denser graph, which can be beneficial.
And the density, the structure of the triangular lattice is key because it naturally supports partitioning the space into 6 equitable angular sectors, right?
Absolutely. The space is easily divided into 6 equal pi slices, each pi over 3 radians wide. Let's call them S sub t indexed modulo 6. This innate order 6 rotational symmetry, which mathematically is known as the dihedral group D6, that forms the linear symmetry foundation of the whole discrete system. And achieving this clear, balanced 6-sector partition is the first major step towards things like load balancing and efficiency in parallel algorithms.
Okay, so the triangular lattice provides the rotational symmetry.
Yeah.
Now, constructing the actual discrete graph, lambda sub r eta, it requires a constraint we didn't need in the continuous world. The inversion circle has to use an admissible radius r.
Right.
What does admissible mean in practice here?
Right, the radius can't be just any number anymore. For the discrete structure to work perfectly, the square of the radius, r squared, must be an integer that can be represented by the specific quadratic form that defines the norms on the triangular lattice. It's $20 plus Manfio plus N22. Basically, in layman's terms, if R is admissible, it ensures that the set of boundary points, the actual vertices on the lattice that make up the circle, let's call them VTR, must form a nice symmetric set. Usually it's a multiple of 6 vertices, forming something like a perfectly centered hexagon, or maybe a dodecagon, on the lattice.
Why is that precise symmetric boundary so important for the discrete version?
Because it ensures that the key element of the continuous duality, that perfect zone swap via inversion, can be carried over exactly to the discrete lattice graph. The graph lambda sub r is constructed such that the inner set of vertices, v minus r, is the exact image of the outer set of vertices, v plus r, under that circle inversion map iota sub r. This construction guarantees that the number of vertices inside, size of v minus r, is exactly equal to the number of vertices outside, size of v plus r. You get perfectly balanced, perfectly dual zones in your digital model. It's a perfect symmetry.
And the edges, the connections between vertices, they must also obey the duality rules somehow.
Yes, absolutely. The edges maintain the topology, the structure of the connections. Edges within the outer zone, V plus R, are just the standard length 1 lattice connections you'd expect on a triangular grid, nearest neighbors. Edges within the inner zone, V minus R, are induced by applying the inversion map to those outer edges. Now, geometrically, the inner edges end up having variable lengths. They actually get shorter as you get closer to the origin. But the critical point is that the adjacency, the connectivity structure, is perfectly preserved. Topologically speaking, the inner subgraph and the outer subgraph are isomorphic. They have the exact same connection structure, just geometrically warped or scaled.
Okay, isomorphic subgraphs. That sounds powerful.
Yeah.
So all of this complex structured symmetry, the 6-fold rotation from the lattice, the reflections inherent in D6, and this new radial inversion, it's all unified under one algebraic umbrella. A symmetry group. The triquarter inversive hexagonal dihedral symmetry group, which Schmidt designates as T24, T sub 24.
That's right. T24 is the group that governs the entire discrete framework. It captures all the symmetries simultaneously. And let's break down why it's so powerful and why it's order 24. It essentially fuses 2 distinct types of symmetry. First, you have the linear symmetries of the base triangular lattice itself. That's the order 12 dihedral group D6. For listeners who might not have dealt with group theory recently, D6 simply describes all the ways you can rotate or reflect a perfect hexagon and have it land back exactly on itself. It includes 6 distinct rotations, 0, 60, 120 degrees, etc., and 6 distinct reflections across different axes. 6 plus 6 equals 12 operations. That's order 12.
Okay, D6 covers the rotations and reflections. What's the second component that gets us to T24?
The second component is the new radial nonlinear symmetry provided by the circle inversion map, iota sub r. Remember we said it's an involution. Applying inversion twice brings you back to the start. So iota sub r is an order 2 operation. It has 2 states, original and inverted. When you mathematically fuse these 2 types of symmetry, the linear D6, order 12, and the radial iota sub r, order 2, you generate the full group T24. 12 times 2 is 24.
So we have a total symmetry set of 24 distinct operations, various combinations of rotations, reflections, and inversions that all preserve the underlying structure of this discrete graph, lambda sub r.
Precisely. That's what T24 represents. It's the complete symmetry fingerprint of the system. And this group structure ensures that the framework's key properties, especially those directional phase pairs we defined way back in section 1, are maintained consistently across rotations, reflections, and the inversion operation. This is what Schmidt calls equivariant encoding. It's a really important concept.
Equivariant encoding, what does that mean in practice?
It means that if you calculate some property or assign some label at a vertex, and then you apply one of the T24 symmetry operations, like rotate 60 degrees, then invert, the property or label at the new location must transform in a predictable, systematic, and structure-preserving way dictated by the group operation. The encoding respects the symmetry. This is absolutely essential for designing robust, advanced algorithms that need to maintain perfect symmetry compliance, especially in physics or structured data analysis.
Okay, so the theoretical groundwork of the T24 symmetry group and the lambda sub r lattice, it seems like it provides immense potential for real-world applications. Let's look at the deep consequences of this structure now, starting with something called bijective self-duality.
Right. This is basically the operational payoff, the practical result of that Escher reflective duality we discussed earlier, but now applied rigorously to the discrete lattice graph. Schmidt's theorem 4.32 formalizes this. It states that the inversion map iota sub r is not just a bijection, a perfect swap of points, but it's actually a graph isomorphism between the inner zone subgraph, lambda minus r, and the outer zone subgraph, lambda plus r.
Graph isomorphism. That means they're structurally identical, right? Same connections, same number of neighbors for corresponding points, just different physical locations and edge lengths in the plane. Why is that revolutionary for computation? What does that let you do?
It means that any computational task, think pathfinding algorithms, like finding the shortest route, or maybe clustering analysis, or even just indexing data structures. If you perform it in the outer zone, you can perfectly mirror the result in the inner zone simply by applying the fast inversion map iota sub r to the inputs and outputs. You do not have to run the expensive computation twice, once inside and once outside. If the graph structure is identical, the computational result must be structurally identical. You just map it across.
That is massive. That sounds like it leads directly to guaranteed reversible information preservation.
Exactly. Think of it this way. If you define some complex function or build a data structure in the outer zone, you can perfectly reconstruct the identical valid function or structure in the inner zone just by applying iota sub r. This is incredibly crucial for things like fault tolerance and efficiency. You could use this duality for perfect checkpointing, for instance. Save the state of a long-running algorithm in one zone, and you instantly have a mirrored, valid backup state in the other zone. Or think about perfectly undoable operations in some editing software. You could reverse a complex process without any approximation or error because you have a guaranteed bijective twin state readily available via inversion.
Okay, that's impressive. Now, to navigate and measure distance within this perfectly symmetrical space, the framework apparently utilizes two specialized distance metrics. And again, these metrics are specifically engineered to be self-dual, meaning they are invariant, they don't change, under the circle inversion map iota sub r.
That's right. The first one is the simplest to grasp, the discrete dual metric. Let's call it d-hops. This is simply the shortest path distance, measured in the number of steps or edges, the hop count, between two vertices within a single zone, either inside or outside. And because the inversion map guarantees graph isomorphism, the number of hops between any 2 points A and B in one zone is exactly preserved when A and B are inverted to their twin points A' and B' in the other zone. It's a measure of adjacency, of connectivity, that completely survives the reflection. The hop count is the same.
Okay, hop count is invariant. What's the second metric? You said it was more complicated.
Yes. The second one is the continuous dual metric. Let's call it d sub h. This metric is derived from hyperbolic geometry, which is a type of geometry uniquely suited to modeling spaces that have a kind of constant radial curvature, making it perfect for this circular framework where distance from the boundary matters.
Hyperbolic geometry.
Oh, yeah.
Okay, how does it work here?
The key concept Schmidt uses is something called boundary relative depth. He defines a variable, let's call it magnitude u, which is based on the logarithm of the ratio of a vector's norm, its length, to the radius r of the circle. Let's try to unpack that conceptually without getting lost in the logs. Instead of measuring distance in just absolute Euclidean terms, like inches or meters from the origin, this metric measures how deep a point is relative to the boundary circle t sub r. Using the logarithm has this nice property. It effectively scales the distances. Movement near the boundary, where things are spread out by inversion, is treated as computationally equivalent to movement near the origin, where things are compressed by inversion after you apply the map.
Okay. So if I take a small step far away from the boundary circle when I'm in the outer zone, its inverted equivalent, which will be near the origin in the inner zone, is also considered a small step far away from the boundary in that relative sense. And the d sub h distance for both of those corresponding steps remains the same.
Precisely. The continuous metric d sub h is also completely invariant under inversion, whether you measure the distance between 2 points in the inner zone or the distance between their inverted partners in the outer zone using this metric. The d sub h distance value remains exactly the same. This kind of invariant continuous metric is really essential for building stable, invertible data structures that need to handle geometric scaling smoothly.
Right. And these two dual metrics, the discrete hop count and the continuous hyperbolic one, they enable a really powerful practical application. Mod 6 sector and radial bin bijection hashing. That sounds complicated, but it seems like this is where the initial encoding established way back in section 1 truly pays off for indexing.
It's basically a highly efficient indexing or addressing scheme. Remember those directional phase pairs assigned back in section 1? They defined which of the 6 angular sectors, modulo 6 the original vector belonged to. That's the mod 6 sector part. And now we also have this invariant depth, magnitude u, from the d sub h metric. That gives us the radial bin part. It tells us how deep the point is relative to the boundary. So a vertex can be identified by a unique key composed of these two components, both of which are invariant under the circle inversion. Its angular sector 0 through 5, and its dual norm bin, derived from that invariant depth magnitude U.
And because the key itself is inversion invariant, made of invariant parts, you can use that same key to look up a point or its partner in either dual zone simultaneously.
Yes, exactly. That's the beauty of it. It allows for incredibly rapid, constant time lookups across the duality. Imagine a process is running in the outer zone, and it needs to retrieve a piece of related information stored at the corresponding point in the inner zone. This dual invariant key structure allows the system to instantaneously calculate the storage location or address in the opposite zone without any recomputation or searching. Just apply the same key structure. It makes both zones instantaneously accessible and searchable using the same logic, leveraging the symmetry for potentially massive speed gains in data retrieval.
Okay, that's clever. Finally, let's discuss what seems like the ultimate payoff in terms of parallelism: equivariant encodings and conflict-free parallelism. You mentioned equivariant earlier with the T24 group. Equivariant functions assign labels or values that consistently transform when symmetry operations are applied.
Right. And the triquarter framework uses a particularly advanced equivariant encoding called the trihexagonal 6 coloring. Now, the standard triangular lattice graph has a well-known 3-coloring property. You can color all its vertices using just 3 colors such that no 2 adjacent vertices, neighbors, share the same color. Schmidt merges this basic 3-coloring property with the even-odd parity of the angular sectors, modulo 2, whether a sector index is even or odd. Combining these two pieces of information generates 6 distinct color classes for the vertices on the lambda suburb graph.
Okay, 3 colors from the lattice structure combined with even-odd sectors gives 6 colors overall. Why is having 6 colors better than 3 for computation?
Because of the specific geometric properties of this carefully constructed trihexagonal 6-coloring scheme. Just like the 3-coloring, in this 6-coloring, no 2 adjacent vertices, no vertices connected directly by an edge share the same color. Therefore, each of the 6 color classes forms what's called an independent set in graph theory. All vertices of the same color are not adjacent to each other.
An independent set, meaning you can process all nodes of the same color at the same time without them interfering with each other. So you can partition your computational load based on color.
Precisely. Imagine running a parallel algorithm like a breadth-first search, BFS, to explore the graph. With this 6 coloring, you can potentially run computations on all 6 color classes simultaneously, assigning each color class to a different processor or core. Since no 2 adjacent vertices share the same color, you completely eliminate resource contention and race conditions between the parallel tasks operating on different colors. You can process 6 different non-interacting parts of the graph at the exact same moment without any collision or conflict. This offers theoretical speedups of up to 6 times for algorithms that can be parallelized in this way. It's a direct application of harnessing the lattice's inherent D6 symmetry fused with the radial duality to optimize digital hardware performance to its theoretical limit based on that symmetry.
Okay, the theory sounds incredibly powerful. 6 times speedup is huge. But the theoretical structure of the triquarter framework needs backing up. Did Schmidt provide empirical validation? Simulations showing these real-world efficiency gains in the discrete domain on that lambda sub-R graph?
Yes, he did. The second paper includes benchmark results. The first test case focused on directly exploiting that bijective self-duality. They called it inversion-based path mirroring. This is a direct test of the graph isomorphism between the inner and outer zones we just discussed.
Okay, and the method seems straightforward enough. You calculate the shortest path between 2 points, say A and B, but only in the outer zone, using a standard algorithm like BFS or Dijkstra. And then instead of running the whole algorithm again to find the path between the inverted points A' and B' in the inner zone, you just instantly mirror the outer path result using the fast iota sub-R bijection map.
Exactly. And the consistency of the results reported here is quite powerful. Schmidt's simulations consistently yielded approximately 2 times speedups, about 2x, in the total path computation time, compared to the standard method of calculating the path from scratch in both the inner and the outer zones separately.
So you essentially get 2 paths for the price of roughly 1 full computation, plus a very fast mapping. Think about the applications there, maybe in distributed systems or robotics. Imagine a mobile robot operating in a highly symmetric environment, like a specially designed factory floor, or maybe a specialized symmetrical network topology. It could calculate its optimal path from a central hub out to one symmetrical region, and then instantly replicate that optimal path to the symmetrically opposite region without wasting precious cycles on recalculating the complex traversal algorithm. It's like getting instant replication of optimized results across symmetry lines.
It's a very practical demonstration of the duality. The second benchmark focused on symmetry-reduced clustering. This one specifically exploits the rotational symmetry, the Z6 part of the T24 group.
Okay, how does rotational symmetry help reduce the calculation load for something like clustering?
By simply avoiding redundant calculations for points that are symmetrically identical, Schmidt computed complex network metrics, for example, the local clustering coefficient, which measures how connected a node's neighbors are to each other.
Yeah.
But he only computed it on one representative vertex per rotational orbit. Since the graph lambda sub r is guaranteed to be rotationally symmetric under T24, specifically under the D6 subgroup, the result for that single representative vertex must be identical for the other 5 vertices in its 60-degree rotational orbit. So you compute the value just once, and then you simply replicate that result across the other 5 symmetric copies. No need to recompute.
Wow, so you're literally using the structure to just eliminate 5 out of every 6 required computations for rotationally symmetric properties.
Exactly that. And on larger graphs tested in the simulations, this technique achieved computational reductions of up to approximately 6 times about 6x in computation time for tasks like global clustering analysis or motif counting. This is obviously invaluable for efficient analysis of highly structured or symmetric networks where structural repetition is common. Think of certain chemical molecules, crystal structures, or maybe even some types of social network models.
Okay, so stepping back from the benchmarks, what are the broader implications here? This triquarter framework, it really feels like more than just an academic exercise in designing neat lattice graphs. It seems positioned as a foundational tool for optimizing pretty much any system that relies fundamentally on circular symmetry and precise directional properties.
I agree. The potential scope seems impressively vast. Schmidt himself points to potential applications in really fundamental physics, like potentially deciphering the quasi-normal modes of black holes, which often involves complex analysis in partitioned domains around a central point. For signal processing, those efficiency gains in conditional checks we talked about earlier, they could mean immediate enhancement of computational performance in existing signal processors or algorithms.
And in the realm of computing security, what about cryptography? You mentioned the T24 symmetries. That sounds like it could offer huge potential for lattice-based cryptography, which is a big area for post-quantum security.
It could, yes. Exploiting these high-order symmetries inherent in the framework might significantly reduce the computational cost of key generation or certain operations in some lattice crypto schemes. That reduction is often a major hurdle in deploying these secure, quantum-resistant protocols efficiently.
Interesting.
Furthermore, think about quantum computing itself. Phase relationships and boundary conditions are absolutely critical there. This framework provides a highly structured, phase-aware method. It might be useful for optimizing qubit modeling or simulation, especially across interfaces or boundaries where phase coherence is key. And then, more generally, you could see potential to improve efficiency, accuracy, and scalability in areas like multi-agent coordination systems, like drone swarms and formations, advanced medical imaging devices like MRI or CT scanners dealing with cylindrical or spherical data, and perhaps high-performance wireless communication networks that rely heavily on beamforming and directional signal control.
It covers a lot of ground. But despite how comprehensive this 2-paper set seems, Schmidt does note that there are still significant open challenges for future research, right? It's not a closed book.
Oh, absolutely. Primarily, he mentions the extension of the framework to higher dimensional spaces, moving beyond the 2D complex plane into spaces like C to the n, multiple complex dimensions, or trying to apply it to other complex manifolds, like the surface of a torus or a sphere. Those remain active areas where the power and applicability of this specific duality structure still need to be rigorously proven or adapted. So yes, the work is certainly groundbreaking, but the journey of fully exploiting these kinds of symmetries has clearly just begun. So I think the core takeaway from this deep dive is really how profoundly efficient computational systems can become. When you start treating geometry as just a passive backdrop, a stage, and you start treating symmetry as an active, exploitable resource, as a computational tool itself, the triquarter framework By successfully integrating those generalized coordinates, the phase pairs, and these powerful T24 dualities, it provides a rigorous and, importantly, an executable path to potentially superior computational speed and also information conservation through that perfect reversibility. Schmidt's real genius here, I think, lies in taking structural symmetry, elevating it to a formal algebraic group, T24, and then using that group structure explicitly to eliminate redundant work and simplify control flow.
It really is like the ultimate shortcut, isn't it? But one that's built on the most rigorous fundamental mathematics. It fundamentally restructures how we might think about designing algorithms for space in a digital domain, especially symmetrical space.
Exactly. And maybe one final point to tie this back to the future of research itself. Schmidt specifically mentioned in his notes that the creation and refinement of this intricate framework were, interestingly, assisted by his use of the AI tool Grok. But he emphasized something crucial, that the real key to using AI effectively in highly technical disciplines like mathematics and physics is not allowing the AI to just generate the ideas wholesale, but rather it lies in the human researcher's ability to creatively and rigorously question, prompt, and apply the methods of science and mathematics against the AI's suggestions and outputs. The human guides and validates.
Using AI as a powerful interactive assistant, not a replacement for rigorous thought.
Precisely. So here is a provocative thought, perhaps, for you, the listener, to carry forward. Given that this tricorder framework relies so heavily on exact bijective principles, on perfect symmetries captured by T24, how might the strategic integration of symmetry-aware AI tools, AI that is perhaps built from the ground up to natively understand and leverage these complex bijective frameworks and group structures, how might that combination accelerate the rigorous pursuit of scientific discovery across traditionally challenging, highly structured fields? Think high-energy physics with its fundamental symmetries, or crystallography, or material engineering where lattice structures are everything. Could symmetry-aware AI be the next leap?